the simulation world over into the operations side and really take advantage of those simulations. So we have, like I said earlier, we have a great list of presenters here with us on the webinar, and I'm just going to go through and show this next slide. Just shows you the agenda. We're going to really providing the context. We have Mohammed Hadi he is from Florida. He is from Florida International University, where he is. Dr. Hadi is a professor there, and he has 35 years of experience in this research community in TSMO, ITS, traffic simulation, and data analysis. He's really been involved in a lot of great TSMO-related research projects since the 1990s. He co-chairs the Transportation Research Board on traffic simulation, that committee, and he's a past chair of the Joint Simulation Subcommittee, SIM-Sub, and he's a member and past member of other TRB committees. So we're happy to have Dr. Hadi. We also have with us Phil Mesher from Iowa DOT. Mr. Mesher is currently a transportation planner and project manager in the Iowa Department of Transportation Project Management Bureau. His primary responsibility there includes being the project manager for Iowa's Interstate Investment Plan and leading an international multidisciplinary advisory team that focuses on the maintenance and update of the interstate plan. We also have with us Mr. Joe Blasi from HNTB. Joe has over 17 years of experience as a transportation planning engineer and project manager for the Kansas City office of HNTB. Mr. Blasi founded and leads the firm-wide transportation planning modelers user group, which connects over 100 HNTB modelers to share modeling knowledge and experience. And in addition, we have Sahiti Lahara from Virginia. So she is actually employed at the Virginia DOT. She is a PTOE with over 24 years of research and professional experience in traffic planning, modeling, design, performance measures, and data analysis in at both the private and public sector. She co-chairs the TRB Standing Committee on Traffic Simulation and sits on different traffic operations related NCSRP panels. And she's got definitely a wealth of experience in this industry, so excited to have her with us. We also have Britton Hammett with Kimley Horn. Britton is a transportation engineer at Kimley Horn in DC, primarily supporting projects related to data analytics, multimodal planning, traffic simulation and modeling, and intelligent transportation systems. So Ms. Britton studied ITS at the Technical University of Vienna in Vienna, Austria, where she received specialized training in traffic simulation modeling, multimodal ITS, and data analytics. So that's our list of speakers today. Thank you so much. We have 146 attendees right now, so great attendance here. Thank you for being with us for this topic. So we have a great series of presenters here that we're going to get into. We're actually going to start with Dr. Hadi. And just a couple of housekeeping notes. If you have any questions or thoughts as we go along, please don't hesitate to use the chat pod to get those out there. We're actually going to go through kind of a roundtable discussion, Q&A at the end. So please, if something comes to mind, don't hesitate to use that chat function. But now, just welcome up Dr. Hadi.
Thank you, Brad. And I'm happy to present in this because this is really an important topic and very close to my heart. And my presentation will be in two parts. One part is my thoughts on the role of benefit and traffic simulation in TSMO. And the second part is to go quickly about some of the applications that we have done through the years in FIU on this topic. Simulation is an important part, we think, of TSMO and supporting TSMO, and it can be used hand in hand with data. So I think data has obviously data analytics is an important part of TSMO, but if we combine that with simulation and traffic analysis, that will have extended strength by having both advantages and disadvantages of both platforms or ways of doing the analysis. So to appreciate the role of simulation, I think it's good to connect it to different decision processes that traffic management and operation is having. So we had a project with the FSWA that we done recently that look at that framework of the decision-making process and then look at the decision support by using different traffic analysis methods that use data analytics and simulation and analytics. So the decision can be obviously divided into strategic decisions which set the direction for the agency at the strategic level. But then we have the tactical decisions which involve decisions on the project and investment and what are the activities that need to be done at the tactical level, at the tactical manager level. And then obviously we have the operational decision which that include developing response plans and deciding when those plans will be implemented both in real-time operation and in offline operation. So that's a framework that we developed for as part of the FSWA project. Includes 6 layers. You could see here the strategy layer is an overall layer that look at what are the strategies that the agency would adopt from freeway management, different type of freeway management to arterial management, to incident management, to freight management, and so on. And then you have a performance layer that look at the performance measures or metrics that the agency would adopt to determine how effective are those strategies, and then the tactics and the operational activities that are done to support the strategies. And then you have the 4 layers, the vertical layers. One of them is the people layer, which we need to have the right people to do the data analytics and the simulation and supporting the decision, even IT stuff. And then you have the process layer, which includes both the decision and the analysis process in addition to data governance. And then you have the platform layer, and there we have the data warehousing and the real-time decision support system, but also we have those simulation and data analytics tools. And then finally the data layer, which is an important component that feeds both the data analytics and the simulation analytics. And when you think about it in that process, you could fit the simulation in a nice way with everything else in that big decision-making process that we are talking about today. There are several types of analysis that need to be done to support TSMO. That include descriptive analytics to determine what is going on in the system, diagnostic of why these things are happening, predictive analytics, which predict the future condition, both in offline analysis and also in real-time online traffic management center type of analysis. And finally, there is descriptive analytics where we assess what if scenario, and that can include also optimization techniques that determine the best way to go with this type of analysis. So simulation fits very nicely in all of these 4 applications. And as you go down from the prescriptive, you see that the simulation can start playing more and more part of the pie in supporting those type of analytics. And as part of that framework that we developed, we identify different methods to support the analysis, and that range from different machine learning to statistical techniques, and then simulation and analysis is an important part of that. And if we don't have simulation as part of that, we think that the analysis will not be complete to support the decision-making process. So what are some simulation used in TSMO? Important, obviously, is pre-deployment before implementing certain TSMO applications. You want to see if this ramp metering is going to be effective in reducing congestion, or adaptive signal control is going to work in this type of environment. But also a post-deployment evaluation. As one of the FSWA projects on ICM, in fact, found out that when you do before and after analysis, a lot of time you also want to complement that with or supplement it with post-deployment evaluation to see what are the benefits of the deployment, because sometimes things change in real time that you in the real world that you cannot control based on data, and using simulation will support, for example, COVID. When you do before and after, and the COVID situation happened, the data will not give you the actual delta in terms of performance measures. Offline design of plans and update to this of the rules that is used in the activation. This can be based on judgment, but be optimized. You want to test those under different conditions, and simulation can play a major role in that. Determine the cause of congestion. A lot of time what we face is that there are many bottlenecks that are interacting with each other, and it's very difficult to isolate based on data of what is going on. And a lot of time, sometimes it happened to me even when I started doing simulation, we had an assumption of the problem happening at one location, but when we solved the problem in that location, we found out that we're creating many problems downstream. So that's very important to do before deciding on a course of action. Training traffic management center personnel on what to do when certain things happen and what is the impact. I'm going to show one of the projects that we did on that. What are the impacts of their decisions or their actions in the traffic management center on traffic operation? Predicting the performance in real-time operation, supporting the design and assessment of CAV application. And this is really important, considering that CAVs we don't have a market penetration of it now that we can accurately assess their impact on the network. Providing data on parts of the network that do not have sensors. And imagine that we have a big network and we don't have sensors, travel time or volumes on every part of the network, especially on the arterial. So some of the simulation applications can be used to estimate those based on origin destination matrices and based on what is partial sensing of the network. And then finally, one of the applications that we have used in several of our projects is to generate data to train machine learning. If we do just machine learning based on current data that we collect from the traffic sensors, we don't see a lot of things that will happen, especially if we have a new plan that's going to be activated that are now not activated, or if we're going to have a different design of the network. So using simulation to generate data is an important aspect of this. But doing simulation for TSMO also has certain requirements and require advanced methodologies. So one of the things is the need for multi-resolution analysis for some of those projects, where you want to look at the strategic behavior of the drivers of diversion and maybe multi-modal where they shift to transit and so on. In addition to micro simulation, at the operational level. There's also need for multi-scenario analysis. By multi-scenario analysis, we mean that in TSMO, the effectiveness of many TSMO strategy happen in incident condition or bad weather conditions or construction conditions. So you want to have clustering analysis to cluster the condition in the network. And then you do the simulation for different scenarios, and you'll have better feeling of the impacts of TSMO strategy. The calibration of the behaviors of the travelers in general is an important. It is important for other applications, but it gets more complexity when we deal with TSMO, especially when you have information system, onboard vehicle units, and so on, where the driver react to, and you want to determine how those drivers and travelers react to these messages and information. And then how the replicating TSMO and CAV applications. So even the technologies themselves and is coming from different OEMs. The automated vehicle are different for so how to replicate those in a best way in simulation, how to replicate different adaptive signal control strategies in simulation. So that's another complications or extended capability that needs to be added. And then we need data analytics and model integration. We also have to pay special attention to the tool that we are going to use to support our analysis in the right way. More and more, the analysis, simulation analysis, starts to get to an advanced concept, and in recent years that have even start to be maturing and are going in the direction of mature applications. So those include software in the loop, where you can bring, for example, a controller firmware and install the software on the same computer and run the micro simulation model. Co-simulation, the FSWA has been working on co-simulation. For example, you could have simulation of cooperative, adaptive, cooperative driving automation with autonomous driving automation, with communication, with the traffic simulation. So you can have 4 or 5 different simulation environments that interface with each other. Could have hardware in the loop, and I'm going to show you just one example of what we are doing in FIU. And then vehicle in the loop, you can have the vehicles either in the real world driving, and that vehicle is interface with the simulation environment. Or you can have a human in the loop, where you can have the driver in a traffic simulator, where the driver sits behind a wheel of a car, either in the simulator on the real world, and look at the behavior of that driver and the environment. So that part, the first part, I hope gives some background of what simulation can do to support TSMO, and what are the features of simulation that need to be considered and enhanced to be used in an effective way to support TSMO applications. I'm going to talk now in the second part of my presentation about some of the examples that we did at FIU through the years on TSMO simulation projects, and a range of things that can be done. Obviously, other researchers in the United States and overseas have done a lot of work, but I wanted to focus on our experience at FIU in that aspect. So this was done in a project that we did 2010 to 2011 as part of the Department of Transportation project. This project, we integrated, at that point in time, we integrated CORSIM, which was used even more than now at that point in time. As part of the SunGuide traffic management software of the FDOT, and we look at it from two different perspectives. One of them, SunGuide was in the early or in the beginning of the development stage to incorporate drivers from different sensors. So what we produce is a module where we feed the virtual detectors from the simulation to the central traffic management software on corridor in Miami, and allow the software to make decisions based on those virtual detectors, and then find out if the different modules of SunGuide work the right way and respond the right way. Another objective that we did is to, you can see on the right, is to show when an incident happens, how much is the delay, how long is the queue growing, and what is the impact on traffic. And at that point in time, the DOT project manager asked us to do that because they wanted to show this to their employee or the operator at the traffic management center, to tell them that each minute, 2 minutes, 3 minutes you are delayed in doing this is how much delay we are getting due to a delay in incident clearance of lane. This we've done a lot of projects on freeway management application. 2 or 3 different projects. Some of the of real-time activation of route metering area speed limits based on the probability of breakdown. So before the breakdown happens, we determine the probability that it will be a breakdown in the traffic, the stochastic nature of the breakdown happening. And then we activate the route metering versus what would have been done by the system, which was depending on traffic operator sitting at the traffic management center and observing the traffic. So we compared the two, and we found the benefit of activating the route metering using prediction, and the prediction could be based on machine learning too, or based on traffic flow theory. Acceleration requirement on meter graph. I have a slide after that, and also activation signal plans when the queue back signal on, and then also assessing merge area safety impact using surrogate safety measures. So this is an interesting application where the FDOT, again, this is an FDOT project, was concerned about the truck. We had ramps that had heavy trucks, and for ramp metering, they were concerned about the inability of the trucks to accelerate if we put the stop line of ramp metering in certain locations on the ramps. And what we had to do at that point in time is to calibrate the truck performance based on the real world truck acceleration and power to weight ratio and so on, and we put that in the simulation model to reflect the actual real world truck behavior rather than what is in the default in the simulation platform. But then that gave us the option or the capability to compare 5 different options, including maybe doing preemption for trucks or bypass lane or pushing the stop line back. And that's before we even implemented the ramp metering, and this was for in Broward County in Florida. We also had another application is we use the signal timing plan during arterial events. So we combine, we automated expert decision using fuzzy logic and decision trees, and then combine that with high resolution controller data, and we fed that all to a simulation environment, and we optimize the best option when there is incident on the arterial, either lane blockage or urgent demand on the arterial, and then that allow us to compare different performance in terms of delay and queues and throughput, and then we selected the best approach to do that for the facility that we are looking at. This here is another project where we looked at the diversion during freeway incidents, and we predicted the diversion using, again, machine learning based on data, and we combined that with the simulation modeling to determine the impact on the alternative routes, and we activate special signal timing plan, what would be the impact on the alternative routes. And we use, in that case, solution simulation to confirm the effectiveness of the optimization. This developed for freight signal priority and transit signal priority. We wanted to look at both freight signal priority and transit signal priority the same corridor. And what we've done is first to, again, calibrate the simulation model truck behavior to replicate the real-world truck behavior, and then we ran simulation multiple times, and we fed the results to a decision tree machine learning platform, and that gave us basically some threshold of when freight signal priority is preferred and when transit signal priority is preferred, considering different performance metrics that we identified in the process. So this is another example of using machine learning in combination with simulation, data and simulation, to support a certain application. And this one, we worked on I-95 managed lane in Miami, and the FDOT at one point in time changed the toll on it. So what we wanted to see is simulation model can kind of predict. Okay, I just want some water. A simulation model, dynamic traffic assignment, can predict the shift between the general purpose lane and the express lane due to that shift. So we look at the data before the change, and based on the data before the change, we came up with a model of the behavior of the driver, how much they are willing to pay under different traffic congestion. Then we incorporate that model in dynamic traffic assignment and compare the results in the after condition, and we saw that the model is able to replicate very closely what was the shift in demand between the general purpose lane and the managed lane after the change was made by the FDOT. So we were very happy and kind of, very happy that the model that we developed was capable of that, because it's a challenging kind of application. This is connected vehicle-based red light violation warning application, and this is again one of our recent TRB papers. And if you look at this, you see that when we started looking at the red light violation warning using the microscopic simulation model that we used, we were not able to find the benefit of the red light violation warning, because it was the behavior of the driver at the dilemma zone were not correct. But then we calibrated the simulation model based on real-world behavior, distribution of traffic behavior at the dilemma zone. And when we did that, we were able to show the benefit of red light violation warning application under different conditions in terms of reduction in conflict and improving the safety of the drivers, and also the impact on traffic operation. And I mentioned that hardware, driver and vehicle in the loop simulation is becoming an important component of our analysis. And here I show a picture of our lab in FIU where we have that connection between the simulation and the controller and roadside unit. And we think that more and more as the application becomes more complex, we will need to have that type of these type of environments, integrated environments that can help looking at the vehicle application, the controller application, and the roadside application in the right way, and rather than just emulating their behavior. So this is the last slide. Then I want to mention another project that we are doing with FHWA on developing a traffic analysis capability maturity framework. I know that the TSMO community is very familiar with the TSMO capability maturity framework, and considering the success of that, the FHWA wanted to have that same type of framework, but applying it to traffic analysis to improve the capability of agency in doing traffic analysis. So we started actually on the left which is this 6 dimensions should be familiar, or all the TSMO agency knows this 6 dimension of the TSMO capability maturity framework. We started with that, but then with stakeholder involvement in the traffic analysis community, we look at now 8 different dimensions with 25 sub-dimensions. We are about to finish that report, and as part of that, we have incorporated advanced simulation of advanced strategies as within the capabilities of that are required or needed for agencies. We hope that at the same time the TSMO CMM will I know that there are several TSMO CMS will also include components that incorporate more the simulation and traffic analysis to support the different decision processes of TSMO. So I think this is my last slide, and I know that Brad, you said that the question will be toward the end. Okay.
That's right. Thank you, Dr. Hadi. Really good presentation, helping set up the context of what we're talking about, and showing some examples. And now we're going to have Joe Blasi and Phil Mescher. Joe is with HNTB and Phil is with Iowa DOT. Come up and talk about further going over TSMO strategies and actually use cases of utilizing simulation. So, Joe and Phil, you ready to go? Can't hear you yet, Phil. Are you there? Joe, are you there?
Can you hear me now? Can you hear me?
I can. Yep. You're there.
Oh, okay. Great. Let me word there for a second. This is Phil Mesker with the Iowa Department of Transportation, and very happy to share experiences that we had here with a project on Interstate 380 in Iowa. to look at TSMO analysis. Switch slides here quick. So today we're going to really focus on, how did we use simulation modeling to analyze, the benefits of TSMO. Iowa's a fairly rural state, and, we have congestion. It's not quite like maybe some of your big cities. We have, mostly it's the different types of non-recurring congestion. That's about 70% of what we have in the state of Iowa. And our peak hours are very short, not even quite an hour in some cases. But we were happy to try to utilize simulation to look at how this could benefit. So a little bit about our corridor. So this is a commuter route that's between two fairly large cities in Iowa. One is Cedar Rapids, and that's a population of about just over 250,000. And Iowa City is about 170,000. So this is a very short corridor, relatively speaking. It's about 16 miles between the two. And we have a lot of commuters go back and forth. Cedar Rapids is a little bit more of an industrial type community. Iowa City is the home of University of Iowa, and they're well known for their hospitals. So there's a lot of development that's been happening in between as well. So it's been very fast growing. We've jumped from about 38,000 ADT in 1998 to most recently here in 2018 to about 63,000. So that's greater than a 3% jump, per year. So we've been monitoring the congestion. We know it's getting worse. We were looking for ways to mitigate what's happening there. And so this is really a great test bed for, how could we use TSMO strategies to combat some of that. And so we were really able to use simulation modeling to do this. So we're looking at, this is basically a 4-lane corridor the whole way between the two communities. So we're looking at, how can we extend the life, at least capacity-wise, of this corridor. So what we were able to test is we looked both at freeway management and then also arterial management with this project. So freeway management really looked at a lot of dynamic lane and speed control. We do have, a lot of times where we'll get queues that back up from slow-moving traffic. So we looked at some queue detection warnings. Even though this isn't quite, your really solid urban type of environment, we still looked at ramp metering, which was really good. And then hard shoulder running, too, to try to temporarily expand that capacity for us. And then, of course, we looked at, investigating crash sites, too. And the arterial management was also just as important, so we have to deal with traffic signals and clearing out queues and things like that. So the advanced and adaptive control, signal controls was something we really tried to focus on. And then, too, there's emergency vehicle preemption. We do get, accidents and crashes along this corridor. And then access management, too. So local turn restrictions were something that we tried to focus on quite a bit as well. So that's kind of an overview of what we looked at. So I'm going to turn it over to Joe to actually get into the simulation details, and then I'll close out a little bit later. Joe?
All right. So, I'm going to start talking about why the software that we used was Transmodeler and why we used Transmodeler. Dr. Hadi talked a little bit earlier about different model fidelities, resolutions, and we wanted to leverage Transmodeler's ability to simulate in a hybrid environment. So Transmodeler allows for microscopic and mesoscopic and macroscopic fidelities. We also, by using a hybrid model, we were able to model a larger area and keep the computing time at a reasonable level. Also, Transmodeler has a TSMO module built in, so it makes it very easy to test certain TSMO strategies. And then finally, we use Transmodeler because we were building this off of a TransCAD demand model, and so there were some efficiencies there. So we built this starting with the Iowa statewide iTram model, travel demand model, like I said, in Transcad. And you can see that on the left image on the screen. And you can see with the little red square where we're zoomed in here on east central Iowa, and the image on the right is the sub area that we cut from that statewide model and what we modeled. So Cedar Rapids is up at the north end, and Iowa City is down at the south end, and I-380 is the corridor in between. It's highlighted in blue, although I realize that's very difficult to see. When we first built this model, it was not just to look at TSMO and I-380. It was built to look at several high priority projects in both cities. So it was important to be able to have a model that encompassed this entire area. It's probably close to 40 miles top to bottom here, so it's a pretty large model area. Let's see, and like Phil said, so we're going to focus in here on I-380, the I-380 corridor. So I mentioned before the different available model fidelities. For this particular model, we focused on the micro and the meso levels. Micro we used on the freeway itself, so we could get the full level of detail and look at the effects of the TSMO strategies. And then we used the mesoscopic resolution in other areas. We wanted to make sure that we could still capture vehicle diversion around the corridor, but didn't want to bog down the model with all the computations. This is just showing a little bit of coding in the model, how you set the different segments to the different fidelities there. Okay, and now the fun part. So this is when we got to test some of the different incidents that we dreamed up. We developed two different incident scenarios. One was an hour-long scenario in the southbound direction of I-380, and another one was a 30-minute incident in the northbound direction. And for these tests, we implemented a strategy of hard shoulder running only in one case, and then another time we looked at hard shoulder running and added in active lane management. So by that I mean like the green arrow that you see over the sign on the image here, and the variable speed limits that you can also see on the sign. So I'm going to jump into detail on this 30-minute incident in the northbound direction that we modeled. So more specifically, we closed the outside lane and the shoulder for that 30-minute duration. We allowed for hard shoulder running on the inside shoulder, and then, like I said, in one of the scenarios, it was just the hard shoulder running, but in another scenario, we did implement that active lane management as well. And so now, Nilu, if you could switch over to the video, please. I'm hoping this is going to be not too choppy for you all. Now I'm going to walk through we have some of the screenshots or some of the video from the actual simulation here. All right, so we start down at the south end of the I-380 corridor at I-80, and quickly here we're zooming into the start of the hard shoulder running lane in the northbound direction. The darker blue color on the inside shoulder, that's that hard shoulder running lane. And you can see the time in the simulation toolbar just crossed 4 o'clock, and you can see the vehicles now starting to use that hard shoulder lane, which we turned on at 4 o'clock. Here we're seeing the actual incident area that's showing up in red here. So at 4:15 we said, okay, the incident's going to begin, and you can see the vehicles now starting to move over to the left and use that hard shoulder lane to get around the incident. And you can see the queues starting to back up. Here you can see we've zoomed out a little bit. queues continue to back up. This is showing the active lane management with the 2 inside lanes open and the outside 2, they're trying to get traffic out of it. And here we have some ramp metering going on the upstream on-ramp. Now here it's almost 4:45. We're about to clear the incident. There it goes. And then you can see all the vehicles, you kind of open the floodgates and let them go, and you start to see the queues dissipating. Now here we are back at the south end. All right. So here are some of the results that came out of that model run. You can see across the top we compared our future no build. So we did also run the incident with the lanes that are out there today, no hard shoulder running. And then we ran it with the hard shoulder only, and then the hard shoulder plus the active lane management. Down the left side here you can see some of our MOEs. Level of service, we looked at 4 different segments along the corridor. The incident that we placed on the corridor was between I-80 and Penn, so that first row there, and then the other segments are actually the downstream segments after the incident. And then you can see VMT, VHT, et cetera, and some travel times. When we look at the results here, it was kind of interesting that the future no build, of course you have poor level of service at the site of the incident, but then we had poor level of service downstream of the incident, and what that was really representing is once the incident cleared, like I said, you kind of open the floodgates and all the vehicles then move downstream. That's when you get the poor level of service downstream. Is after the incident is over and all those vehicles are now propagating downstream. You can see the hard shoulder only, that really helped what was going on downstream. Of course, you still have the poor level of service at the incident itself. And then the scenario with the active lane management, this was kind of a surprise that we saw some poor level of service just after the incident. And in looking into it, it really was more of a case of where we had the variable speed limits coded, and so even after the incident, we kept the speeds low for a time, and that's what led to the poor level of service for that segment. I mentioned the VMT, VHT, but I do want to highlight a little bit the travel times there. You can see the northbound I-380 travel times. We saved about 10 minutes with the hard shoulder running scenario. Here's just another way of looking at the data. This is a heat map of the densities along the corridor. So up and down are north and south along the corridor, and then to the left and right are times. So with the future no build, you can see the big red blob is all the congestion that builds up behind the incident, and then you open the floodgates and you see the higher density that occurs after the incident downstream. And then with the hard shoulder running and with the active traffic management added, you can see that you're really helping the congestion. It doesn't go away, but it helps it. And then with the active traffic management, you can see that little tail on it after the incident. And like I said, that's due to that dynamic speed control. So I'm going to turn it back to Phil real quick to just talk about what we did with these results once we had those.
Great, thanks, Joe. Appreciate that very much. So obviously we do this analysis so we can figure out what we're going to do with this corridor. We definitely learned that the simulation was a great tool to show us what the TSMO strategies would reveal for us, and there's definitely some benefits there. And so much so that we have more TSMO or integrated corridor management studies that are ongoing now. There's one in Des Moines, our capital city, Des Moines, Iowa, that's a huge study going on where we're looking at a lot of different TSMO strategies. So with this corridor, though, so as we started to take a much deeper look, we have some asset conditions that we have to take care of. So pavement condition has really been struggling. This is probably mostly original pavement from the 1980s when this corridor was initially constructed as part of the interstate program. So as we looked at this, we determined that we're still probably going to need to do quite a bit of reconstruction. And looking at the costs, it really makes sense that they're pretty close. So we're going to go ahead and it looks like at this point to reconstruct the 6 lanes. Now, however, as the traffic keeps growing on this corridor, this certainly does not preclude any TSMO strategies to be implemented along this corridor. And then, of course, we also are going to look at the downtown area soon across 380 in the town of Cedar Rapids there on the north end. So I'm sure that that's probably going to have some really good strategies and opportunity to look at, what TSMO can do for us and use simulation to do that. So lots to look forward to here in Iowa. So that's all we have for you today. Appreciate your time very much.
Thanks, Phil and Joe. Great presentation. Now we're going to welcome. Thank you. Now we're going to welcome up Sanhita in Britain to give us a presentation from VDOT and Kimley Horn.
Good afternoon. We will tag team the presentation like the last presentation, Britton and I. I am Sanhita Lahiri. I manage the Data and System Analysis program. I'm very happy to bring you this instance of simulation in TSMO. I will just start with the challenge that we had at hand. The challenge was that we have a section of I-95, and actually a very big section of I-95, which is near the Fredericksburg area, starting between Richmond and Northern Virginia, which has a very complex travel behavior and a mix of commuter with long distance travelers, and then it has high density and it's very incident prone, along with very high unreliability. And this is also the corridor which is traveled by a lot of, senators and, Congress people and everybody. So it's a very high visibility and often complained about section. So we have studied this section for quite a bit. Then finally we came to the conclusion after studying the patterns of speeds and volume and all that variable speed limit would be a good strategy to implement in this section. So the way that we decided we would do is we did an extensive search in other areas in this country where variable speed limit was being implemented, and what were all those challenges in those areas, and we quite didn't see any parallel to what we were trying to do here, or even the challenges that we had here in this I-95 corridor section. So basically, what we had to do was build our own algorithm based on the speeds here and based on the volume and the volume density and all that here. So we basically had to create our own algorithm. That's the one part. Then the other part is actual deployment, how all this data would be collected, handled, and then, of course, test it so that, it doesn't create more problems when it gets deployed. It doesn't create more problems than, solving the problems. So there are lots of pieces to all of this. And then, of course, continuous monitoring, looking at other things like return on investments, how, on the first day of deployment, drivers don't quite know what to do about this. Over a period of time, how is the compliance and things like that. So there's lots of considerations and pieces to this. So we actually decided, instead of taking this very big, long section, we decided to do a pilot project for a 15-mile section. And that's the section that you are seeing there. And hopefully the benefits that would be realized after that is faster, reliable travel times, and of course improved safety, as we have a lot of both primary and secondary crashes in this section. So how would we do all of this? We would, kind of have detectors placed at strategic locations, and often enough, so they would collect these volume and speed at 30 seconds interval, because all this is would happen on a real time basis. So they would collect data at 30 seconds interval, and then this data would kind of get crunched through the algorithm, and then recommendations for speed would go back to the field, and then they would update the signs. That clicked. Okay. So that's those are the stepwise, derive the traffic conditions, go through recommended speeds, and finally there will be posted speed limits. And then we would have periodic updates of this. There are also guidelines that are there based on how the smoothing of this can be done, both spatially and temporally, of these posted speed limits. You can't change it too often, or you can't change it too fast between the signs, because it kind of takes a little bit of reaction time for the drivers to absorb all of this information and then, kind of react to it. So this is how, all of this, the basic concept is supposed to work. So what's, like I said briefly, so then first we will have the assessment. We have the assessment that where we could deploy this system, where it will make the most sense. Then the analytics part, then we would look at the performance part, see whether the improvements are happening or not, and if not, tweak it based on that. And then, of course, the results, what are we getting out of this? And then the continuous maintenance and update of this, test the effectiveness of how the algorithm is working. Do we need to, because this has not been deployed widely, how do we need to tweak some of these things, even though there are certain guidelines set for, how often you can update some of these speeds, whether it is effective or not. And then, of course, Virginia has, the seasons, like there might be snow on the ground at some point in time. Is it effective then? How is weather impacting? How is visibility impacting? Some of those we might not have data at the granularity that we wish, and then how to absorb these multiple types of data and then bring it into it so that we can make an informative decision out of that. And based on that, calculate the posted speed limit and then bring it back to the drivers. So lots of things happening. And then all this complex system that we are actually creating ourselves, this algorithm. Before we go and deploy it into the field, we will have to test it. That's where the simulation plays such a critical role. Not only that, some of these detectors that we talked about, it's not in the field right now. So all we could have was bring in some data into the simulation environment, generate a feedback loop out of the simulation environment, and see whether these algorithms actually work or not. And things like driver behavior and the decision making, all of this needs to be adjusted within the simulation environment based on what the drivers do in the field in that section of roadway. That's how all this, we are kind of learning from the simulation, and then trying to adjust and tweak the algorithm. That's that part. And then also the simulation also generates data which can be fed into the algorithm itself to kind of work that part. So it's kind of both sides used. So with that, I will hand it over to Britton Hammett, who is from Kinghorn, and she will take us through some of these inner workings of the model itself. Britton?
Thanks, Sanhita. All right, so we're going to dive into some of the details about this microsimulation environment that we set up to test the variable speed limit algorithm that we're deploying on Interstate 95 in Virginia. So what does our model look like? We created a VISM model in VISM 11, and it represented a 4-hour analysis period that was determined from the highest 4-hour demand on an average day. So we collected field data, and we created this baseline model. And we coded it with vehicle inputs that were updated, that update every 15 minutes based on collected detector data, and ramp volumes were estimated from using streetlight data. So a VSL site is comprised of vehicle detection and speed limit signs. So in the field, that's what a VSL site looks like. And so our goal was to create a VSL site that was as equivalent as possible in the simulation model. So all 24 VSL sites were represented in their approximate locations based on our actual design plans in our VISM model. Data collection points in VISM were used to collect lane by lane, speed, volume, and occupancy at 30-second intervals to reflect the Wavetronics detectors that we'll have out in the field as they're deployed. And then we used desired speed decisions to represent speed limit signs. One of the things that we played around with a lot was the spacing of the data collection points and the speed limit signs to represent a driver's sight distance to those signs. We used field data to create the baseline empirical speed distribution with the baseline speed limit of 70 miles an hour. So we gathered existing field data and created this baseline speed distribution. However, another challenge that we ran into was how do we select a speed distribution for a lower speed recommended by the algorithm when the algorithm changes that speed based on a downstream congestion event, for example. And this is a challenge because we don't know how the drivers will react to the speed postings prior to deployment. And so we tested a number of different assumptions, including using a mirrored distribution to match the 70 mile an hour field empirical distribution, but adjusted it according to the new posted speed. So as you can see in the images on the top right, for 55 miles per hour and 45 miles per hour, we have the same shape of distribution, just consolidated based on the actual posted speed limit. So then similar to our previous presentation, we wanted to make sure we represented a few different congestion events or road closures. So we created a number of road closure scenarios that would result in congestion along the interstate corridor. For our baseline model, we coded 3 different closure locations with 1 and 2 lane closures on the right and left sides of the highway, just to test a variety of different scenarios. In VISM, we coded these lane closures with overlapping links and partial routes that allowed us to only activate the road closure for short periods of time throughout the 4-hour simulation. So in the images you see on the screen, the orange lines represent the locations where the lane closures occurred, and the green lanes represent merging and weaving links with dedicated behavior types to ensure realistic lane changing behavior occurred with these road closures. So this model was not calibrated in the same way as a lot of our large traffic analysis models are typically calibrated due to the modeling objectives being different, as well as the lack of available data for full calibration. And so, however, we made a few different tweaks to the driving behavior from the VISM default driving behavior to more accurately reflect lane changing in particular. We wanted to make sure at these congestion events that we were testing our algorithm on, that they are as reflective to real conditions as possible. So as I mentioned previously, a freeway merging and weaving behavior was created with adjusting car following behavior of the a little bit of car following behavior, and then some of the cooperative lane changing behavior and deceleration thresholds. So while we didn't have field data to specifically inform what those driving behavior changes should be, we did use guidance developed in the VDOT TOSAM as well as the VDOT VISM user guide and VISM 11 evaluation that all really contributed to a better understanding of driving behavior in these models for the Virginia region. And so if you haven't checked out those resources, I definitely recommend you do so. So bringing it all together, we're not going to play a video here, but you can imagine this moving across your screen. But bringing it all together, this video or this rendering shows that the algorithm working in real time. So we have the corridor going from in the northbound direction from south to north, and what the graphic on the right shows are all of the different recommended speeds that are happening actually in the middle of the algorithm based on the real-time simulated data. And so what this is intended to represent was that by coding in our VISM model, integrating that into a loop with our Python algorithm, we were able to see every single intermediate step of all of our different steps of our algorithm, from just what are the traffic conditions to what are we recommending based on that one location to what are the smooth ultimate posted speed limits. And we were able to see all of that through this process. So using the data from running the algorithm with the simulation, we were able to create a dashboard that will run live when we actually deploy this VSL system that details the system, the algorithm, and the VSL system's performance. So without running the algorithm with simulation, we would not have been able to collect meaningful data to begin populating this dashboard until field devices were deployed. And so we've been creating this dashboard for more than 4 months at this point and refining it, getting feedback, and making sure that it's communicating valuable information and starting to understand how the algorithm is working with the simulated data. And only actually this week, we're starting to get field devices out in the field in advance of when we go live with the system. And so this has given us a huge benefit to advanced development of some of our software tools prior to field data being available. And it's also given us just substantially more time to refine these, get feedback, and go through that procedure. So at this point, Nino, if you're able to share the video, I want to just watch this video really quickly. But the development of this dashboard with simulated data has given us tools to better explain how the system is going to operate. And so this performance simulator that we're going to see on the screen was taken from our dashboard, and it depicts the simulation and algorithm data aggregated every 5 minutes. So what you're going to see is that every 5 minutes through our 4-hour simulation, we're going to see slight changes. So on the top graph, we have the average speed that's traveled by simulated vehicles. And the black line is the actual posted speed limit. So what we can see here is how the average speed that we're projecting is changing in relation to the calculated posting speeds. And when average speeds reduce, that's because of one of our lane closure locations. So in this graphic, the x-axis is representing the corridor. So the left side is the south end, the right side is the north end. So this is showing that progression of traffic from left to right as drivers navigate from the south end to the north end of the corridor. We also see at the bottom the changing dots. These are showing various states of traffic. So green, good, free flow, red, bad, congestion. And the size of the dots represent the density. So as the dots get bigger, we have a more dense segment. So some of the things that this has been really helpful to see is that we're effectively seeing that we're predicting that the algorithm is effectively predicting various components of we're ahead of drivers when they need to reduce their speed, and we're ahead of drivers when they need to increase their speed. And so that gives us a lot more confidence in our algorithm even before we test this with field data. And it gives us the ability to have gone through all of these testing procedures prior to field deployment. So we can go ahead and switch back to the slides. So this simulation testing environment not only allows us to stress test the algorithm, but with realistic traffic data in the near exact configuration that it will be deployed. But it also gives us the opportunity to evaluate system performance to anticipate the benefits of the system and how those benefits may change under different conditions. So we are collecting performance measures information such as the number of stops, the average speed, the travel time, and the throughput. And as you can see on the right side, we're comparing these different metrics at different time periods throughout the simulation. So this is one example run that we've conducted recently where the blue is representing the baseline without the algorithm, the conditions as it is today, and the orange is representing with the algorithm. And it's showing us the percentage of stops, a total number of complete stops that drivers are making. So we can see in this rendering that the algorithm is effectively smoothing out traffic so that fewer drivers are required to come to a complete stop, which could have both operational and safety considerations. We're also reviewing the impact of compliance on the system. We're trying to answer the question of how much compliance is really needed to maximize our system benefits. And so for this analysis, we're reviewing high and low compliance rates by adjusting various vehicle types in VISM to represent different distributions of drivers following various posted speed limits. And so this is, again, one of the challenges that we're facing is there's a lot of different ways to define compliance and what is high compliance? How do you represent that in a model so that it is realistic? And so that's one of the things that we're making assumptions and forging through on as well. So I would say from the modeling perspective, our greatest challenge is that there are just so many assumptions required. We need to make assumptions on driving behavior because we don't have resources for full calibration. We needed to assume speed distributions for vehicles following the VSL system when they reduce speeds, and we don't have a good baseline for what drivers are actually going to do. We needed to create congestion events, closing one or two lanes at varying distances and at varying locations. And we also needed to work around various modeling quirks that we don't have time to go into today, but if you guys have some, I would love to hear about them. But I think that's one of the things that is really interesting from the modeling standpoint is that we have to be very careful as simulation modelers to make sure that our assumptions are accurate so that we're getting a valid result. And this is no different. While we don't have a fully complete calibrated model, we still want to make sure that the assumptions that we're making are valid and are going to be telling us a realistic story. And so I'll pass it back to Sanhita for some big picture conclusions as well. I think, Sanhita, you're muted if you're speaking.
Yes, I will.
Perfect.
Yeah, thank you. Okay. So we took you on a deep dive of how, the intricacies of algorithms and modeling, steps and all that. And the reason why we kind of wanted to give you a little bit glimpse into this internal thing is to, kind of show you how some of these things are very critical in TSMO. For example, Britton mentioned that within the VISM environment, she placed the detectors at a certain distance based on, sight distance, etc., and also where those input is needed. Now, how does it translate directly? It translates to the design of the corridor itself and where we put all those posts. So these other things. So that's the reason why we want to kind of stress that how this is so important in needs of TSMO. But just stepping back, there are also, I think, while we were going through this process, some larger needs from our research partners. We could, for example, for this, use some predictive analytics based on the crashes and safety when some of these crash could occur and when the lane closings would happen, and kind of how more randomly input that into the system as opposed to quote unquote staging it. Some of the CAV and TSMO where they kind of come together, how say cooperative adaptive cruise control, how can it impact say, and this is just an example I'm giving, this variable speed limit, does it impact or how the driver behavior changes? People will basically have to be driving on a manual mode without going into these automated systems, without deploying these automated systems. Does that impact compliance? So all these things are where we need a lot of feedback from our research partners. So with that, I kind of wanted to bring you back to, why we are trying to do this kind of webinar series and get some conversation about the cross-section of simulation and TSMO.
Thank you, Sangeeta. And thank you, Britton. Very good presentation. So now I'm going to welcome up Chris Milson with LSU, Louisiana State University. He is the program manager of Louisiana Local Technical Assistance Program, and he's going to help guide us through a short Q&A period. So if you haven't already, put any questions you have in the chat, but he's actually going to get us started. So Chris, can you come off mute? Can you hear? I don't hear you yet, Chris.
Brad, this is Nilo. I believe he was just trying to redial, so he will need a minute to get on the audio.
Okay. Okay, well, we'll see here. I have a list of questions, and then maybe he can pick up here in it. So maybe I can't see the chat, Nilo. I don't see do you see any questions in the chat right now, Nilo?
There was a question that was sort of answered in the chat while the other presenters were going on. Yeah, I wasn't sure if there was anything Joe or Phil wanted to expand on. Okay.
Well, one question kind of goes back to Sangeeta. What can be done to better bridge the gap between TSMO and modeling communities? That's part of the reason why we're here today in this webinar. So maybe if you could each talk a little bit about that.
Yeah. Thank you for that question. You're right. That's why we wanted to kind of have this. I think some of these areas of TSMO, the other thing that I didn't speak, for example, was why we cut off the simulation at these edges of the project. We should have or could have gone a little bit larger because to see what's happening upstream and downstream and how those are affecting or impacting this, right? We didn't because this was a fast turnaround project, like all TSMO projects are. So we had to quickly give some answers. So it would be helpful, for example, if this were a multi-resolution model and there were some efficiencies that the research community could build into these simulations, like more driver behavior types that can happen during these, more assumptions that can kind of guidance on assumptions that can be made during these when these applications are running. So definitely we need the researching community to be partners in this. That's me wearing my DOT hat, wearing my researcher hat. I would say that we are at that place. We are very ripe for all of these research to happen, and all we need is some, backing and championship from the state.
Yeah, I guess I would just add on I very much agree with everything Sangeeta said, and one of the things that I think would really help increase the usage of simulation for TSMO applications is making it easier. just making some of those assumptions just more straightforward. And the only way you can do that is through more experience with it. And so as we do more, it will become easier and faster and less resource intensive to be able to plug in your variable speed limit or your hard shoulder running or other various applications into a model. And once we have a more streamlined process for that, I think that will really help bridge that gap.
Okay, this is Chris. Can you all hear me now?
Yes, we can hear you, Chris.
Yes, we can.
Yes, Chris.
Okay, I apologize. I literally had one job, and I failed at that one job. So I apologize. But Brad did have to leave. I know we're still kind of doing the Q&A. I do see a question in the chat for both Britton and Sanhita. And this is kind of a detailed question about the code. But would it be possible to share their source code for the algorithm they developed and if the dashboards were developed in Python? And Sanhita answered that in real time.
Yeah, I can.
Real-time operation.
I can answer source code of the algorithm we are not able to share at this point. Ultimately, it will be public. Right now, we are going through an entire process of vetting through right from our transportation secretary to the various levels and all that. So I guess at some point in time, but not now.
And the dashboards themselves were actually developed in Power BI. Just to finish answering that question.
Thank you. Listen.
Sure, thanks. And I think before I was an idiot and I hung up the phone, I think Brad, again, kind of wanted to reflect on the purpose of the webinar. And again, Sanhita, at the end of your presentation, you also reflect on the purpose of the webinar. Again, it was to show the potential of traffic simulation and how it can support TSMO strategies. And just to kind of reflect upon everything that we heard today, the first presentation by Dr. Hadi was showing, the unique capabilities of traffic simulation. Again, how that can serve in analyzing TSMO applications when sometimes other things can't. For example, the data that you can actually collect right now. And then again, we highlighted with the use cases by both Iowa DOT and Virginia DOT and how they have used simulation to analyze TSMO strategy. So actually, I'm going to flip the Q&A because we just have 4 minutes. And also kind of briefly mentioned by Sanhita, the idea actually is hopefully to make this as a webinar series. And so we can highlight more applications and more things related to simulation, how it supports TSMO. And again, the purpose was this is the introduction, again, introductory webinar. So for the folks in the chat, actually, I have a question. What would you like to see in the second, or in the series of webinars, for example? Are there specific TSMO applications you'd like to see, specific simulation case studies you'd like to see highlighted? Or what else would you like to hear discussed in more detail that wasn't discussed in this presentation? So while you're all thinking about that, and again, we do appreciate if you have any feedback on that, I think I'll ask maybe one more question to the panelists. Again, kind of getting back on track on the purpose of the webinar. So I think, Brad, again, I hung up like an idiot, but I think you already discussed about how you can bridge the gap between the TSMO and modeling communities. Another question, which I hope you didn't ask yet, was how can simulation perhaps be more formally integrated, which is kind of a follow-up to that first question. How can traffic simulation be more formally integrated into the TSMO project process?
Well, here, this is Joe Blasey. I can start. I would say events like this are really good at getting the word out about the benefits of simulation in analyzing TSMO strategies. We both case studies today showed videos, and so just having that visualization that you can see what's happening goes a long way when you're talking to decision makers and the public. So I think that's a huge benefit. And then the ability to just test different scenarios. I think Dr. Hadi touched on that earlier. In a simulated environment, you can try anything, and you can see what it's going to do. So that's obviously a huge benefit of the traffic simulation.
Chris, this is Mohammed. Thank you. One thing that I think need to be done is right now, if you look at long-range plan or PD&E studies, design studies, you have manuals and handbooks that describe how analysis can be used to support this. And I would say that one of the things, after we learn how to do things, and we have case studies similar to the one in Iowa and the one in Virginia, several of these case studies, and we have lessons learned, it would be great, I think, if we can work on incorporating traffic analysis as part of manual and handbook. I know that AASHTO is working on a transportation operation manual that will be released in the near future. And if those type of manuals have chapters on analysis to institutionalize that process, I think that would be something that will take us in the right direction.
And if I can add to that, what Mohammed said, that the other part of this is that return on investments and efficiencies. So, and this is to the developer community and the research community, is that how can we make simulation for TSMO? Simulation for planning is a little bit looked at different way. The data, the timeline, it's a little bit different, and that's what has been done so far. Simulation for TSMO, it has its own nuances, own challenges, own needs. How can the development and the research community make this more efficient?
Absolutely. No, I think those are great comments, both Mohammed and Sangeeta. And I think we are out of time, unfortunately. I, again, want to thank all of the presenters. That was very well done. And also thank all the attendees. We really had great attendance for this. And again, that kind of does show the interest in both of these communities kind of moving forward. So just as a reminder, again, this was sponsored in one way or another by the AASHTO Committee on Transportation System Operations, by the ITE SimCap community, and also by the TRB Standing Committee on Traffic Simulation. There's a few comments that that have been posted that I think are also important information. But with that, I think I will conclude the webinar.